Hi everybody, and welcome back to Digital VLSI Design. I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and today we'll be going over the Kahoot for Lecture 5, Timing Analysis. So we have 12 questions for this quiz. Let's start by marking the correct answer about positive skew. So, positive skew helps us meet max delay constraints. Positive skew makes it harder to meet the setup constraint. Positive skew is good for hold timing, or none of the answers are correct. Well, I think I'm going to go with the first one. Positive skew helps us meet the max delay constraint. And how did I get to that? Well, let's go back to the lecture slides, and we have this really nice kind of summary of setup and hold constraints. And we know that the setup constraint, we have to have the clock period is plus the capture time, or the whole capture time, which includes the clock period, has to be larger than the launch time. And for hold constraint, the launch time has to be larger than the capture time. So let's look at positive skew in terms of setup constraints. And we see that the general capture time will be, the clock period plus whatever the skew is of the clock, because positive skew, we said, is how long the difference is between when the clock arrives at the capturing register minus the time it arrives at the launching register. That's what we defined as positive skew. So t plus delta skew is actually the capture time, and that has to be larger than the whole delay on our launch path. So that's going to be the register propagation delay plus the logic propagation delay plus the setup time plus all kinds of margins that we can stick into here, and we'll be discussing throughout the course. So as we can see, we want this to make this bigger, right? We want to have whatever's on the left side be larger, and positive skew will only help meeting this constraint. So going back to our Kahoot over here, that means that positive skew helps us meet the max delay constraint. Okay, so that's really important. We usually call this useful skew. So question number 2, mark the incorrect answer about static timing analysis, STA. STA is exhaustive, i.e. it checks all the possible paths. STA is only useful for synchronous design. STA does not require dynamic vector generation, and STA ensures correctness of circuit functionality. So which of these is incorrect? Well, in this case, I'll be going on the green answer down here. So let's understand why that is, and we'll go back to our slides for that. So let's talk about static timing analysis. Static timing analysis checks the worst case propagation of what we say are all possible vectors for minimum and maximum delays. Okay, this is, as it says down here, exhaustive. In other words, every single constrained timing path is checked. I think that's one of the most beautiful things of all the algorithms and all the things that we have here in this course. Really, we have millions, maybe more than millions of paths in our design, and we check every single one of them, and we do it really quickly at the click of a button in most of the timing tools we have today. So that's really cool. We do not need dynamic vector generation. However, it does not check circuit functionality, okay? It just checks, as we saw, a kind of a graph that doesn't know what a NAND gate or a NOT gate or so forth is. It doesn't check the circuit functionality. It checks our constraints using just the propagation delays through the different nodes and vertices. Okay, another thing is that it's only used for synchronous designs. We can't use this for all kinds of combinational feedback loops or asynchronous timing issues and so forth. Okay, so those are the things that are actually in the Kahoot over here. The first thing is that STA is exhaustive, and that's really really impressive and important and very cool thing. Once we run STA, we know that at least from a static point of view, our whole design is going to work. Okay, it's only useful for synchronous design. So if we have all kinds of asynchronous design approaches or different types of things, we're going to have to take a different approach to validate or verify those types of paths. And I'll tell you the truth, that's why it's really done sporadically, if at all, in common designs that you'll find. STA does not require dynamic vector generation, so that's another thing that's very true. We just give it the the lib files of all of our design, and of course the netlist and connectivity, and the delay that maybe we got from parasitics, and STA will check it. We don't need to go and give it all kinds of stimulus that come in and provide some dynamic state of the design. Okay, but STA does not ensure correctness of circuit functionality. And for that, we have to, use our heads, or do all kinds of things like we can also use dynamic timing analysis with gate level simulation and so forth. But it does not ensure correctness of circuit functionality. Okay, so we'll go to question number 3, and this one's a tough one. Setup slack. Is it T launch minus T capture, hold slack, T launch minus T capture? Is setup slack T capture minus T launch and hold slack, T launch minus T capture? Which one of these is it? Which one of these types of things? So remember, setup is going to be, the capture time minus the launch time, right? And hold slack is going to be the opposite, so that would be this one. So remember, and I'm right. Okay, so again, we'll go back to basically the same slide that we saw before, and we said that setup time is going to be, how do we get this positive? Setup time is going to be T capture, if we move this over to the other side, minus T launch has to be larger than 0, and for hold time, T launch minus T capture has to be larger than 0. So again, what is slack? It's the amount of time that we have between, when our, for setup, when our next clock edge appears, and that we still had margin, in order to capture the data on time. So our from going from one register to the next register, it took us some amount of time, launch time, okay, and our capture time is basically the clock period. Plus whatever time it takes to propagate over to the capture register. So we need to make sure that the time it takes, the clock period plus the time it takes to capture from the capture register is going to be larger than the time it takes the data to propagate through the circuit. So that's going to be T capture minus T launch, and hold time is exactly the opposite of that. Okay. So question number 4. What is the difference between a tickle list and a collection? A tickle list is just a string, while a collection is a pointer. A collection is just a string, while a list is a pointer. They are the same, and you can always use whichever one you want. They are both strings, but given in different formats. Well, that's a kind of a strange question, but I think this is the way it is. Okay, so this is going kind of into, data structures and syntax of Tickle, and how the different tools address these different types of data structures that they have in it. And what we said about Tickle, which is really important, is that Tickle is a language that is built completely on strings. So everything in Tickle is just a string. And I guess when they started to use Tickle for designing the shells of these tools, they ran into this problem that they have different types of data structures, such as cells and pins and nets and so forth, that a string was a too simple a representation for them. It didn't hold enough information. So they decided to make some sort of a struct or some sort of a hash or something like that holds some other properties about the different data structures, such as maybe the pin has capacitance, or the net has capacitance, or some delay through it, or even its geometry and so forth. So they decided to take the just standard Tickle and make a type of a pointer out of it called a collection, and the pointer points to a certain place in the memory, which has the different properties, the different dictionary type properties, like again, the net has capacitance and maybe delay and maybe the wires that make it up and so forth. And they call this, at least in the SDC type of synopsis type language, they call it a collection. And it's very similar to a list. The thing is that when we query such a collection, we are not going to receive, everything in Tickle again is a string, so we're going to be returned a string, but that string is just some sort of hexa type of a value, which is actually the pointer to where that string fits in the memory of the process. So we can't do much with that string. We have to use special helper functions that will go and dive into that string and rip out the part that we want. And we can use things, so instead of using such a thing as for each, which we would use to iterate over, the members of a Tickle list, which is just going through strings with, a space between them to differentiate between the members. We're going to use something like for each in collection, which will go and take the pointer and go and see what the members are inside, and then iterate over the different members of that collection, and so forth and so on. So all of these are similar to our regular tickle functions, but they what they do is they work on collections instead of on standard strings. Now, again, one of the things that's very useful, in my opinion at least, is that when you query a tickle, a collection inside one of these tools, what you're going to get is just a pointer. You can't do much about the pointer. You don't even know what it is. If we say, get cells, and we get a cell and look at it, we're just going to get this strange hexa value. So we can just put a get object name around the get cells, and then it will take the collection and look at the attribute of it called name, and it will return the string that is the name of that cell and say this is my inverter or whatever it is. Okay, so that's strings versus collections. So going back here, a tickle list is just a string, and that is what we said. Everything in tickle is a string. A collection, though, it's a string, but it's a string that's actually a value that is a pointer to the memory of the process. Okay, all the rest are not true. Okay, question number 5. Which of the following is not defined as part of the create clock command? The clock period, the clock name, the clock jitter, the source port of the clock. Well, I believe it is the clock jitter that is not defined as part of the create clock command. And again, let's go back to the slides, and we see that the most important probably SDC command is the one that says create clock. Without a clock, we can't do any timing analysis. Okay, any clock pin, like a pin of a flip-flop, that doesn't get a clock, some sort of a net that was defined under a create clock command will not be constrained. We won't have any type of, the big T that says what our constraint is for our timing. And the same with our skew and so forth to say what the constraint is for hold. So create clock is a really important command, and it defines basically where our clock sources from, where it starts, and how it propagates to all of the clocked elements in the design, all the flip-flops or macros that get a clock and so forth. And that's how it actually creates our timing paths and understands what the constraints are that it has to check under static timing analysis and optimize under synthesis, placement, routing, and so forth to meet timing. So create clock is really essential. We may be creating several clocks in the design, but basically in our simplest, at least, view of this, we have to make one central clock that's going to go and propagate to all of the clocked elements in the design. And for that, we write create clock, and we have to obviously define the clock period, which is our big T in our setup definition. We give it a name, and the name is just a type of a string that's going to be used internally as the name of the collection or whatever it is, the data structure that is the clock. And we have to tell it where the clock is sourced from. And that is usually a main port to the design. It can also be a pin, like an output pin of a buffer or a mux or a PLL or something like that. So we have to define the clock on somewhere where it can propagate from, and that is either an input to our design, which is a port. That's a typical case for either a full chip design or a type of a macro that it gets a clock that was generated somewhere else, or the output pin of a cell that creates the clock if it's from something like a clock divider or a PLL, or just a clock mux that maybe multiplexes between several clocks. So that is the create clock command. So going back there, we do not define clock jitter in that command. There, obviously, everything I showed here, you have to do a man or help on these different SDC commands or look into the documentation. There are many more options, but as far as I know, clock jitter cannot be defined in the create clock command, and even if it can, it's not something that's used. It's defined separately, as we'll see in a second. So question number 6 actually asks us how we define clock jitter in the SDC. So do we use the command set clock jitter? Sounds good. Set propagated clock? Strange. Set non-ideal network? That actually sounds right. Or set clock uncertainty? Well, this is a really tough one because, these SDC commands may not meet. Before it ends, let's choose this one. Okay, that was a bit strange, but, these commands were written quite a long time ago when maybe some of the nomenclature changed, or maybe they had some reasons for it. But we have some important, clock definition attributes and so forth that we discuss for things. And the one to talk about jitter, or any type of this like extra margin, random type of margin, would be set clock uncertainty. We can define it for setup and hold separately, but in general, something like set clock uncertainty 0.2 would be 0.2 nanoseconds on whatever our clock is. And this is the string that we use to name our clock in the create clock command from before. So clock uncertainty is clock jitter. There is no such thing as set clock jitter and other definitions that we just mentioned. Just for the sake of completeness, set ideal network, which I wrote there in the answers, is actually during synthesis we have an ideal clock. It doesn't have any skew. It doesn't have any propagation from one point to the other. So we'll define the clock as ideal. Obviously, it should not be ideal once we build a clock tree later on in the course. Okay, and set propagated clock is the kind of opposite of set ideal clock. It's a command that says, okay, listen, take the clock and it's not ideal anymore. Go through all the buffers and so forth and add their timing and make it a real clock. I think that set propagated clock, basically, at least in ANOVAs, is applied automatically after clock tree synthesis is run. Okay, so set clock jitter was just something that sounds like that should be the command, but there is no such command. Set propagated clock, as we said, does something completely different. And set non-ideal network is not the opposite of set ideal network. It actually doesn't exist as far as I know in the SDC. So set clock uncertainty is how we define jitter. Okay, question number 7. What is needed to model input paths in the SDC? Input skew and jitter, input delay and input capacitance, load, input drive and input delay and output delay. What do we need in order to model the input paths in the SDC? Well, maybe something like, I don't know, maybe input drive and input delay. Okay, so why is that? And this is another important point that we discussed. One of our categories of SDC commands are I/O constraints. And graphically, we look at it like this. Our scope is going to be this design. So we have our chip or our macro, and it's going to have some sort of boundary. So, there's a whole world out there. Something drives inputs. If it's outside the chip, then that'll be through, IOs, through pads and so forth. If it's a macro, it's just going to be through a pin, a port that's just a little piece of metal, that we connect to this block within a larger design. And the same for outputs. It's either going to be an output, to the outside world that's going to go and touch a wire somewhere on the package and so forth, or it's going to be, a little piece of metal that connects to just another net that goes somewhere else in the design. But for simplicity, we're going to hierarchically design this and treat this macro separately. But this is our whole scope. This is what we know about. And when we look at reg to reg paths from one register to another register, where the clock source is at some common point inside the design, we know everything we need to know about this type of a path, right? We have the registers with their delay and their setup and hold. We have the propagation delay of the combinatorial block in between, and we have the entire clock path that gives us the skew or the propagation of the clock. So we have no problem with these reg to reg paths, and luckily, the vast majority of all the paths in our design are going to be these reg to reg paths, and we'll treat them like that. And most of our optimization is going to be done on reg to reg paths. And life would be, I guess, beautiful if all we had to do was just optimize these reg to reg paths, because we really know everything about them. But it's not. We have other people we have to talk to. That's how the world works, And so there's going to be some sort of a timing path outside, both on the transmitting and on the receiving end of our macro. So basically, we need to model these parts because they don't exist. Now, again, this could be something that really doesn't exist because we have many different ways that it can be connected, to different things. If we're going to reuse a block in different designs, so the outer part is going to be, different for the different designs, or if we use, if it's an entire chip, whatever we have outside the chip may be different. If we have a USB port, it might be connected to a mouse or a keyboard or a USB stick. It can be different types of things. So what happens out, but another thing is that even if if this is a block that's being made in a certain specific chip and we're just hierarchically designed this, we are not in charge of this. We don't have it yet. It doesn't exist, and we have to model it. We'll see that there are ways to model it with interface logic modules and stuff that give us a better hierarchical approach in that type of a way when we're doing, this as inside a certain chip. But in any case, we need to model these outside parts in order to run our static timing analysis. And what we need for that is we need to know about the launch path that's outside the chip and the capture path that's outside the chip. Okay, and that needs two things. It needs to know basically what our delay is from the point where the clock starts until it reaches the input of the chip, and it needs to know the transition over here so we can go into the lib file of the driver that's over here. Same thing with the output. We need to know how much the delay is outside the chip until we sample whatever the signal is, and we need to know what the load is so we know our driver inside the chip, how strong it drives the load. So really we need this input drive type of modeling and the output load type of driving, plus the delay that happens outside here. Okay, so those are the two things that we discussed in the Kahoot. We need for an input path, we need the input delay and the input drive. Now, there are different ways of modeling these things. We could say what the cell is that drives this net, and then we kind of can know the drive strength of it through the lib file, or we can set a transition over here, which is just kind of a fake type of a thing, but it will at least give us a good way to set our timing of the buffer that's at the input over here. Another thing is that this whole idea of an input delay, I'm not crazy about it, because the input delay says how much time it took from, I guess this point to this point, or from this point to this point, but it doesn't take into account the fact that we have skew between the clock that arrives at whatever this virtual register over here and the clock that arrives at our design. If they came from a single clock source, which is a must, because otherwise it would be some sort of asynchronous timing path, then there is some sort of skew between the two. And during synthesis and early stages of design, we treat this skew as 0, and that's fine. But afterwards, once we add clock tree synthesis, this net over here will have some sort of a timing delay. And that will be added basically to this capture path in this virtual, this modeled type of a thing. But we don't actually add any propagation delay to this piece of the net, and therefore we cause useful skew that we didn't really mean to plan for. We didn't mean to cause it. The way that the Cadence tools right now take care of this is that they take an average of all the propagation delays of the clock tree into the design and put a negative number on where the actual rise time of this clock net is after clock tree synthesis. That could be, I guess, a way to do it. But I think that the better way to do it is actually not say what the delay is of this type of a path out here, but rather say what the constraint is that we want to meet here. We have a time. Usually, we design with a timing budget. We know that whoever is designing this thing outside has, let's say, half of the clock cycle, and we have about half the clock cycle. So if our clock cycle is 1 nanosecond, let's say set max delay half a nanosecond and try to meet half a nanosecond on this path. By the way, when we finally tie these things together, if it's a hierarchical design, we'll see, this becomes a reg-to-reg path, and we'll be able to check the whole thing. But we want to plan for meeting timing and not having to make ECOs after we actually closed each of these hierarchical blocks. Same is done for the output. In the output, we actually add negative skew, because here, again, this is going to stay ideal with 0 time, and this is going to get some clock propagation, which is going to make us, have the clock arrive at the launch path later than the clock arrives at the capture path, and that's going to be negative skew, and it's going to make our timing harder to meet. Think that if we have a clock propagation delay that's, a whole clock period, then we're never going to be able to meet timing on such a path. And the same being said, if we have a propagation delay of a whole clock period over here, then we're going to have such great useful skew that we don't care what we do here in terms of optimization. We're always going to meet timing. So really, these are the things that we have to take into consideration, and I would rather put a max delay on the input and a max delay on the output, and that's how we would meet the timing. In any case, going back to the Kahoot, input skew and jitter is not what we, I don't even know exactly what that means, I guess. Input delay and input capacitance. So we don't care about the input capacitance. We know what the input capacitance is. That's part of our design. So that's not the right answer. Input delay and output delay. Yes, we usually do define input delay and output delay, despite the fact that, as I just said, I would rather have a set max delay from inputs and set max delay to outputs instead of input delay and output delay. But these are commonly defined. However, this is not the answer to the question, which was what is needed to model input paths in the SDC. What the correct answer is the input drive and the input delay. Those are the two parameters that are needed to define, to model the inputs. Question number 8, which of these is defined correctly? Okay, set false path minus from FF1D minus through ND1A minus to FF2 clock, and then different variants of those types of things. So assuming that FF1 is a flip-flop, do we do from the D port? Assuming ND1 is a NAND, A would be an input port. Do we do through an input pin and to clock port? Let's see. What I think we're going to do here is I think we're going to do this one. Okay. So a false path is a type of a timing exception, and we said because our static timing analysis cannot check functionality, we will have to define such things as false paths inside our SDC. There are different types of things like multi-cycle paths and others in case analysis and so forth that, again, we're going to have to set them manually. And actually, this is a real weak point of the whole constraints, because this is where us as designers are going to be setting something that is really going to affect our timing analysis. And maybe our timing analysis will say that everything's okay, or in a worst case, or in a okay case, but it's going to screw us over, is it's going to tell us that everything's not okay, and it's just because we didn't set a false path. This is a big part of a timing analysis engineer, is going in over the false paths and making sure that false paths are correct or not correct and putting them in the right place. It's something that the timing analysis or back-end engineer is going to be sitting with the designer a lot and trying to figure out. So we had this simple case of like a mux that is the selectors of two successive muxes have some sort of correlation between them, and therefore we can never have a path that goes through the 0 or the 1 pins at the same time of the mux, and it changes what our worst case timing would be. Okay, and in this case we would want to do some sort of a false path, and what we said is that in static timing analysis we have what is called a start point and we have what is called an end point. And start points are either a port, the input port to our design, or a clock. Right, usually it's going to be a clock. So the clock that goes through the register is going to be the start point. Often we just since we don't start at the actual clock source, we're going to set the start point as the clock pin of the register. Okay, an endpoint is going to be the data point of the register or the hard macro or the output port of the design. That's going to be the endpoint. So it would be the D of a flip-flop in general, and all other pins of of cells are going to be just through points. They're going to be internal points on the design. So in this case, everything here we don't show anything as we wanted to show paths through these two muxes, so we said minus through the mux I0 and the mux I0. Okay, going back to our Kahoot then, if we said set false path minus from flip-flop 1D, well, D is not a start point. Okay, yes, we do start from the flip-flop, but the starting point of the flip-flop also includes the propagation delay from the clock to the Q of the flip-flop. So it's not from the D of the flip-flop, it's from the clock of the flip-flop. Through NAND 1A, yeah, that would be correct. And to flip-flop 2 clock, no, we don't end at the clock of flip-flop 2, we end at the D of flip-flop 2, which is exactly what it says here. Set false path minus from flip-flop 1 clock minus through NAND 1A and minus 2 flip-flop 2 D. Okay, so here again we had minus through flip-flop 1D. We can't go through the D of a flip-flop. Okay, and we usually do not go to the A pin of NAND. It's not usually an endpoint because it's a combinatorial path. I guess in some cases it somehow could be. Okay, and here from NAND 1A, again, we don't start from the A pin of a NAND gate. We don't go through a clock pin of a flip-flop. We do go to a D pin of a flip-flop. Okay, question number 9. What is set case analysis used for? So this is another strange type of a thing that we have inside SDC. Well, do we use set case analysis to define a false path, to define a constant value, to define a multi-cycle path, or to define a maximum delay between 2 points? And I know the answer to that. It's to define a constant value. And again, this is kind of a strange thing. I would have chosen different words if I had written the language, I guess. But this SDC language was written quite a long time ago, and it could be that, you know, the reasons for naming things were a bit different then. So what we're going to want to do really is sometimes set constants on different pins. It may be, you know, a port that comes from outside the chip. Let's say we have a fuse, you know, that we want to burn it for a certain type of an operation, or you know, we have like one mode that's a test mode and one mode that's a operational mode, or maybe we have some registers that we're going to set at the beginning of time, and they're going to be, you know, at a certain value, at least when we sell this thing with a certain frequency or something else. So we're going to want to set a constant on what would normally be able to have both, you know, 0 and 1 values, or a bus that would be able to have multiple values. We want to set it at some sort of constant. So we're going to use the set case analysis. And again, looking at the name, you know, this is going to set a certain case for analyzing our design. So for example, if we want to have, you know, the common case, which we'll almost always have, we're going to have some sort of port that's going to say we're in scan or test mode, or we're not in scan or test mode. And then one of them is going to have usually higher frequency, for example, than the other. So we're going to want to have an SDC for, you know, the higher frequency that's going to define, you know, the higher, you know, the shorter clock period, and one for the test mode, which may have a lower clock period. And then each of them is going to have the proper case analysis that's going to make sure that we're not checking timing on the paths that are never going to be operated at that speed and show us all kinds of negative slack. Okay, or alternatively go and try to optimize away, you know, really hard to meet timing paths that are irrelevant. So that's what set case analysis is used for. Okay, and I'll talk about MMC in a second, and if I don't remember to relate to this point, then I'll discuss when we use test case analysis in the MMC. So question number 10, which of these is not a DRV? So a DRV is, at least the way the cadence calls what we say design rule violations. These are not standard DRCs like minimum spacing or minimum width, but they're design rules. They're at the level of the backend. So is it maximum transition of a net, maximum load capacitance of a net, maximum delay through a gate, or maximum fan out of a gate? So which of these is not a DRV? Okay, and the answer is, of course, maximum delay through a gate. So obviously, maximum delay through a gate is, you know, just something that is a characteristic of the gate through, you know, through the lib file. But let's go back again to look at our DRVs. So basically, then the main DRVs are transition, capacitance, and fan out. I would say that fan out is a derivative of capacitance, but it is still something that we like to define in you know, it's in SDC, and we like to define it in our design. So max transition and max capacitance are essential, I would say. Why? Well, remember that when we had our NLDM or our different types of timing models, we always had one, you know, a table that was made out of transition and of capacitance values, and there were for different points that were checked beforehand in SPICE or some other tool, we had, you know, calculations, and for all the points in between, since they're nonlinear models, we would do some sort of you know, some sort of finding, you know, some average in between the values that were in the table. Well, what happens if we have a value that's above the values in the table. Remember, these are nonlinear functions, so we get something that's completely off. So you can never have a transition in your design that is outside the table, that has a transition that is above the maximum transition in the lib file or below the minimum transition in the lib file. Therefore, by the way, these max transitions and min transition, max capacitance and min capacitance, they will actually be defined inside our lib file in the lib syntax. But we can override this in SDC, and there are other reasons to have, these design rules. Okay, first of all, if we have, two slow transitions, then we're going to be very susceptible to noise, to signal integrity noise, which we'll discuss in a future lecture. So we don't ever want to have really weakly driven nets, so we can make the max transition harder. It will also be harder to meet timing, but that's checked by a standard STA. Set max capacitance is the same thing. If we have a really, really large load, then it's probably going to cause a bad transition. So we're not going to usually want to have huge loads. We're going to want to, buffer, clone, and so forth, these types of nets to enable a smaller capacitance. But again, the main thing is to be able to be inside the table, inside the lib files. So we have to be between min transition and max transition and min capacitance and max capacitance for all the nets in the design. Maximum fan out, that's kind of a hand waving type of thing. If we think that we don't want to have gates driving fan outs over 10, 20, 25 or something like that, then because it's probably going to cause a transition and a capacitance violation, then we can set this set max fan out, but it's not really a hard constraint. So maximum transition on the net, load capacitance of the net, and fan out of a gate, those are the basic DRVs. Okay, and number 11, what is the clock period in this timing report? So here's a timing report taken from a cadence tool. Might be a little bit hard to see, but there are all kinds of options here. And we'll look through this timing report, and I will show you that it is actually, in this case, going to be 6 nanoseconds. And let's look at this. Okay, it's not letting me actually show the result here, but I think I have it in this kind of a view. Okay, so timing reports are a complex thing, but they're really important. They have a lot of information, and we're going to look at them a lot. And of course, the actual format that it spit out is dependent on the tool. In a cadence tool and a synopsis tool and a mentor tool, they're going to be different. And number two, it depends on the version you use of the tool, because sometimes they work the function that makes this and it spits it out differently. Plus, we can also configure these timing reports with all kinds of commands to make them look differently. But we really have to know how to read this. And I went over in the lecture about all of these different points of how to read such a timing report, both for setup, for hold, when we have the full clock, and so forth. Just the question over here was, what is the clock period? And Cadence, at least in their newer type of Innovus timing reports, it's a bit cryptic. It doesn't say actually what the T is over here. What it does have is this thing that says clock edge, and we see that the launch clock edge happens at the time 0, and the capture clock edge happens at the time 6, and therefore we can know that the T equals 6 nanoseconds. Okay, so that was the question basically in the Kahoot over here. But really, you should be able to extract every single thing that we learned about in static timing analysis from the header of this report and from afterwards, the content of the timing report. And it's sometimes hard to understand how this plus this plus this plus this arrived at that number, but it always does add up, and we often need to understand that in order to understand where our timing problems come from and how to address them. Okay, and our last question for today is, what is MMMC? So MMMC, is it a smarter replacement for SDC, which is a very old language, a way to define multiple voltage domains for low power design, a methodology to define multiple operating modes and timing corners, or an automation for implementing ECOs? Well, in kind of a way, you could say it's all of the above, but it's actually this one. Oh, I didn't get the click on time, so I missed that question. Maybe I won't be first in this. But let's go back over to see what the answer to that is. So MMMC stands for multi-mode, multi-corner. It could also be called MCMM, multi-corner, multi-mode. Same thing, different company. And remember that the reason we use multi-mode, multi-corner is actually to have a mixture between the fact that we have different modes, like case analyses that we want to run on our design, for example, test mode and functional mode, and we have different corners that we want to check things on, and we want to meet timing differently for the different modes and for the different corners. And so we have this concept of building what we call analysis views. An analysis view is this combination of both, the SDC that we have and the lib files and extraction corner that we're going to use to check them. So it's a way that we can, load different analysis views, different combinations of our constraints and our corners, our operating conditions, and check timing for them and optimize timing according to them. And we do it automatically inside the tool, and it runs fixes and optimizations and so forth, and timing analysis without us having to go and manually load and reload the things. So I mentioned before when we were talking about set case analysis that set case analysis is how we set different modes. We're going to actually have a separate SDC file for each mode. So we're going to have one for test mode and one for functional mode, for example. Using our analysis views, we can set, two different modes to check for setup and two different modes to check for hold, or it can be, very many different modes. So we can basically give a list of all the modes that we want to check for setup, all the modes we want to check for hold, and the tool will know how to go and run static timing analysis on all of them and perform optimization on all of them. It's not exactly concurrently, but semi-concurrently. It will try to, find the best that will meet all of all of these different constraints that we give it without having to go and manually, load and unload these things. Okay, so I did win, even though I missed the last click over there, but we had a good Kahoot in any case. So thanks, and you guys are willing to ask me any question you want on my YouTube channel.